Hi, this is Kiffer with week 6 lecture. If you remember, last week we discussed cross-sectional and case control studies and introduced you to some of the limitations of those study designs. Today we're going to discuss cohort studies, which are the third major type of epidemiological studies. On slide 2, you might recall that evidentiary pyramid, and if you will notice, cohort studies enjoy a relatively high place in scientific research. This is not to say that these studies are without their limitations, which we will get into, but cohort studies address some of the problems with causal ordering that plagued cross-sectional and case control studies. You might remember me saying last week that cross-sectional studies have no sense of temporal ordering, and that case control studies require participants to probe back in time to assess whether they were or were not exposed to any particular exposure of interest. In slide 3, you can see that cohort studies get around this problem by starting with a sample of exposed and unexposed participants, and then throughout time they observe them to see whether or not those who were exposed were really more likely to have an outcome than those who were not. One thing to remember is that these studies can be either prospective, meaning that researchers are conducting the study contemporaneously, or retrospective, meaning that they occurred in the past. Retrospective cohorts can be conducted by looking at hospital or other historical records and examining whether particular groups of exposed or unexposed individuals were more or less likely to have developed an outcome. This is particularly true where hospital records might record the particular exposure of interest, such as if you're looking for the relationship between diseases or maybe hospital surgery outcomes or something like that. On slide 4, you can see an example of a cohort study where participants who are physically active and participants who are sedentary are followed over time, and then investigators examine over the course of time which group had higher incidence of heart attacks. A real-life example of this sort of study is the Framingham Heart Study, which has been conducting follow-up in its cohort since 1969, so quite a while. On slide 5, you can see that the basic 2x2 table is also used in cohort studies. However, it's important to remember that this 2x2 table represents a stronger caliber of evidence, since you actually looked at the incidence in each group and not just the static prevalence like you did in cross-sectional studies. You might also recognize that the formula for the risk ratio is the same as the formula for the prevalence ratio from cross-sectional studies. However, because the underlying data assesses incidence in cohort studies, the risk ratio can actually tell you something about the risk associated with exposure and not just the prevalence associated with an exposure. For example, on slide 6 you can see that in a scenario where an outcome is more deadly for those with a particular exposure, that the cross-sectional prevalence of a disease might actually appear higher in the population without the exposure, despite a higher risk of an outcome in the exposed group. This is why the risk ratio is a more powerful measure than the prevalence ratio, and it's why we conduct cohort studies, in order to characterize incidence, or in other words, risk. However, if you think about this diagram carefully, you will note that cohort studies pose some additional challenges not observed in case control or cross-sectional studies. On slide 7, for instance, you can imagine that a disease not associated with a particular exposure of interest appears to be due to unequal follow-up times among the exposed and unexposed groups. In this example, for instance, you can see that the combination of long induction times and loss to follow-up caused participants 7 and 9 to appear as if they were not diseased, when in reality, had they been followed long enough, they would have eventually appeared to be diseased. This data is said to be right-censored. Right censoring occurs when both individuals are lost to follow-up, or if they've died, or if the development of a disease simply occurs outside the observation period. Likewise, data is said to be left-centered when a disease occurred before an exposure and prior to observation in the study. In cohort studies, participants who have an outcome prior to the beginning of studies are routinely excluded from observation because you're selecting based on exposure status and hoping to observe a development of an outcome. Therefore, the temporal disordering of cause and effect or exposure and outcome is not really always reflected in the cohort study. As with other sources of bias, loss to follow-up is not usually a problem, as it is not associated with outcome or an exposure, or if it occurs randomly among the exposed and unexposed and diseased and healthy participants. On slide 8, however, consider the role that attrition might play in a cohort study. As you know, attrition can occur for many reasons. Individuals move away, they lose interest, or they get sick and die. And because cohort studies require multiple follow-up periods, they are subject to bias based on the motivations that individuals have for entering and exiting the study. Indeed, if individuals exit the study, this may cause us to either underestimate or overestimate an association between an exposure and an outcome. For instance, if you're studying the association between injection drug use and sexually transmitted infections, you can imagine that some individuals might be more or less likely to stick around for follow-up. This would make it difficult to assess whether they developed an STI, and you'd have to omit them from your analyses. However, if the dropout of these omitted individuals was related to an important confounding factor such as age or income or altruism or injection drug use itself through needle sharing, the final estimate would be biased and not generalizable to the larger study population. For instance, if you had high attrition among wealthier participants, perhaps due to the inefficacy of financial incentives for participation, and if these individuals were less likely to share needles, you might find that your sample of exposed individuals overrepresents the number of people who inject drugs from lower incomes and who are more likely to share needles. Starting on slide 9, you can see that there are two measures that allow us to address for the problem associated with follow-up time in cohort studies. The first is to calculate the incidence rate ratio, which compares the ratio of rates in exposed and unexposed groups rather than the ratio of risks between those two groups. If you recall, rates take into account the duration of an observation in addition to the observed number of events that took place. For instance, from our example back on slide 7, we might conclude that there was no difference between the exposed and unexposed groups per unit time of observation, even though the absolute number of diseased participants we observed was higher among the exposed group. Providing another solution, a closely related measure called the hazard rate ratio is commonly estimated in survival analysis. The difference between incidence and hazard is that incidence rates assume that the risk is constant throughout a study. However, you can imagine that as people age or as the duration of an illness moves forward, the risk of certain outcomes changes. For example, as we age, the risk for heart attack increases. And the longer somebody survives with metastatic cancer, the higher risk it is that they will not survive any longer. These differences can impact whether or not the events are observed. Because if somebody dies before perhaps it's observed, or if somebody leaves a study before it's observed, or something like that. Hazard rates address that problem by accounting for both the probability that an event will be observed in addition to the probability that an event will actually occur. In other words, it considers the length of time needed to observe the development of an outcome and represents the rate of an outcome for participants who were observed to develop that outcome. While these two strategies do not necessarily account for the complex sources of bias that underlie most real-world research problems, they are powerful analytic tools that can just about approximate incidence and risk under most conditions that you'll run into. On slide 10, I provide some of the strengths and limitations of cohorts, which I encourage you to review with consideration to those presented for case control and cross-sectional studies in last week's lecture. As you can see, cohorts are vulnerable to some sources of bias and immune to others. Indeed, no study is truly perfect, and even when studies are really well designed, phenomena in the real world often make the study of causality and risk difficult. For instance, on slide 11 I show some path models for two instances of the sort of complexity that might introduce bias into even a well-executed study. The first is confounding and occurs when a third extraneous variable gives rise to both the explanatory and outcome factor of interest, perhaps explaining the association between the two. The second is effect modification, which occurs when there are different effects between different groups, for example by ethnicity or gender or country. On slide 12, I also provide diagrams for mediation and moderation, which are closely related to confounding and effect modification. The primary difference between a mediator and a confounder is that confounders cause both exposures and outcomes, while mediators are caused by explanatory factors and in turn cause the outcomes. Oftentimes these terms are used interchangeably, and maybe the distinction is not so important to some researchers. Moderators, on the other hand, are factors that impact the strength of an association between two variables by interacting with primary explanatory factors of interest. The difference between effect modifiers and moderators is mostly conceptual. Effect modifiers have different associations between explanatory factors and for outcomes for different groups. And moderation represents an interaction between explanatory variables that changes the association between explanatory and outcome factors of interest. However, their diagrams will often look the same, and in practice they have a lot of similarities. But you could probably, if you tried really hard, think of instances in which a moderator isn't an effect modifier and vice versa. Another important thing to consider is that not all variables associated with a given outcome necessarily impact the relationship of interest. These are described as covariates and are not in the causal pathway between the exposure and outcome of interest. An example of a covariate is in the third panel on the bottom left here. Beginning on slide 13, I introduce a number of strategies that can be used to account for the confounding of effect modification or just mediation or moderation. The first of these is standardization, which you learned about in chapter 9, I think. In review, standardization is used to compare two groups with different distributions of confounding variation by applying stratum-specific rates of a study population to the population distribution of a standard population to make them more comparable. On slide 14, you can see another way to account for bias, and in particular to account for effect modification, is to calculate estimates separately for each level of the confounding variable. This is called stratification. For instance, if we want to account for gender and had a sufficiently large sample size, we would calculate separate estimates for men and for women by creating a 2x2 table that separates out the parameters by gender. In the stratum-specific odds ratio, if they're different from the crude odds ratio, then there is effect modification present. In instances where effect modification is a problem, the Mantel-Hensel odds ratio estimates a single summary odds ratio that accounts for the effects of the modifier, or the confounder. In addition to Mantel-Hensel, regression models and other analytic procedures can also be used to test interaction and provide stratified results. Indeed, stratification is widely used and very useful for addressing key confounders and effect modifiers. On slide 15, you can see that regression is also used to control for confounding. In many multiple regression models, a linear equation is fit with adjusted coefficients for each explanatory variable. Each variable on the right-hand side of the linear equation is thus adjusted for each other predictor variable in estimating the predicted outcome across the variables. While you won't necessarily be able to know how these models work, you should be able to interpret the results from a regression model. Usually these results are presented in the forms of an odd ratio, which is just an exponentiated form of the coefficient estimate in some model designs. If you pursue additional biostatistics courses, you can learn about the specific functions and uses of specific types of models like logistic and linear and multinomial models, hierarchical models, and all of that. And you can also learn how to create confidence intervals from these sorts of results, which some of you might be already familiar with. Suffice it to say here that regression analyses are a powerful tool and a common way to adjust for confounding, especially when there are many relationships to consider. Moving on to slide 16, you may have noticed that the first three methods to adjust for confounding discussed so far occur once your data is already collected. However, confounding should not be left unaddressed until the analytic stage of your study. Indeed, this section of the course is about study designs, and as I mentioned last week, confounding and bias are often rooted in the way studies are initially designed. As such, there are three well-established analytic procedures used to control for confounding in the study design stage. These are randomization, matching, and restriction. Randomization reduces the potential for confounding by randomly distributing across all characteristics, thus eliminating both unknown and known sources of bias. Matching and restriction, on the other hand, only address for known sources of bias and do so at the expense of representativeness. Matching does so by ensuring that individuals in the exposed and unexposed groups are matched one-to-one across key confounding characteristics. This ensures that confounding variables are evenly distributed. Similarly, restriction prevents known sources of confounding by eliminating variation of the confounding characteristics and testing the association in only a homogeneous or simplified sample, again at the expense of representativeness. In reality, studies use a combination of these strategies to eliminate the threat of confounding. This is particularly true with experimental studies where matching and randomization, or even all three, are used together. Okay, and with that, I'll leave you to explore the study guide portion of today's lecture. I look forward to chatting with you on the discussion boards and hearing your questions and seeing your responses to some of the study guide questions as you work together to solve this out. Next week, we will add some additional content to study designs by reviewing some study design modifications and getting into how to kind of evaluate study designs overall in the week after. Okay, have a good day.